Hello, this is Ankit Alex Hansda, UR15CS58, and I'm making this video to explain out the program I've made for ninth experiment, that is implementation of binary search tree. So a binary search tree is in a data structure which is a tree, and it has two constraints that each parent has only two childs, and the left child is always smaller than the parent and the right child is always greater than the parent. So using these constants we have implemented this in the program. So for implementation, first of all I have defined a node, a structured T node. This is like to define each node of the tree, and it has three parts. The first is data part. It will store the data, whatever data on the tree, in that node of the tree. Next is left child. This will store the address of the left child of the parent, if there is one. And the right child, this will store the address of the right child of the parent. Next, I have taken a data member. I have initialized root. This will mark the root of the tree. That is, it will point the root of the tree. Then I have few functions here. I have initialized few functions. So let's define these functions. So first is insert tree. So this function, what it does is it makes a new node, like allocates memory to a new node. Then we initialize its value, that is data v. It has like argument which has been passed. The value is passed through argument, and L child and R child is has been initialized as null, since we presently have both right slots and left slots empty. So the first condition we'll check is that if the root is null or not. If it is null, then the element we have just made becomes the root, but if it is not, then we have to append it in the leaf node. For that we have made another function which is called if root is not null. So this is insert function. It's a function which is called recursively, and it has two arguments, that is ptr and tmp. This ptr, it denotes the root, and tmp is the new element which we have just made. After this, first of all we check whether the new element which we have to enter now is less than or greater than the root. If it is less it is less than if it is less than root, then next we will check whether the left child, since it's less than the root, it will go to the left child. So we'll check whether the left child is empty or not. If it is null, then we will make we will append the new element there. But if it is not, then the function is called recursively, and the left child becomes the root, and the element will enter, it remains the same. So this is how we transverse through the tree. Similarly, for the right child we do the same thing. We will check for the right child. If it is empty, if it is not, then we will call the function recursively. So we have now completed our insertion part. Next is our traversal part. So we will make a function like pre-order, in order, and post order. In pre-order, first of all we will check whether while transversing we have argument ptr. Since this is a recursive function, we will have a escape condition, like when ptr is null, that is the argument becomes null. And next what we will do is first print the data, because since it's pre-ordered, it's DLR. So first the data is printed, then it goes to left child, then to the right child. So here first it prints the data, then it goes to the right child, and as you can see it's recursively called. So next time the R child becomes the root and its data is printed, then its left child is gone, then it calls to the left child, and so on and so forth. It goes like that. Similarly, in order the same thing happens. they here, but only difference is that first the left child is called, but and if there is no left child, then this one is function, this one is executed, then right child is then the function goes to the right child. Similarly, in post order same thing happens, first left child, then right child, then data. So we have completed all the main parts of the function program, and one more program is this search one. It will take the element to be searched as an argument, and also the also the root as arguments, and it will check linearly check whether uh, the search element is present in the child or not. And since its return is bool, and since we have taken it bool, so its output will be true and false, which will use to give conditions in the main function. Next is main function. Here we will design a switch case menu, which will prompt the user to insert, print, in order, print, post order, pre-order, or search the element. And as you can see, we have implemented that part. And since the search element has bool output, it returns a bool value, so we will use it in if statement and print whether the element is in the root or not, tree or not. So we have come to our definition of our program. So let's try out our sample. So let's try inserting a few elements, like I'm inserting 1, 2, 3. So it's like currently it's going like this. Since 2 is greater than 1, so it will go to the left child, right child, and 3 is greater than 2, it will go to the right child. So if we print in pre-order, 1, 2, 3 should come. Similarly, if we print in order, should and we know that if we print any binary tree in order, it will always come in ascending order. So as you can see, 1 to 3 is coming, and in post order it will come in descending order, 3 to 1. Now if we try to search, let's try searching for an element like 4. It's currently not in the tree, so it has printed the element is not in the tree. But if we try searching like any element which is in the tree too, it shows that the element is present in the tree. So as you can see, we have successfully implemented our program. Thank you.